Hello and welcome everyone to this session, the PAS session series. So this session is about Cosmology to 2020. So we're going to talk about a little bit about cosmology, what is cosmology and the history, and then most importantly, we are going to be briefly touching about what is happening in this year with respect to this field. So my name is Vadiraj. By profession, I'm into computers and software. And I spent a good amount of time in studying cosmology, which was my childhood hobby anyway. Okay, so it's a good, nice Sunday afternoon. It's cold. You guys, I think you have a good um, environment there at your home, and then having a good hot coffee or a tea at your hand. So let's begin. So most of the slides have some kind of indicator to indicate that okay, we are talking about history or we're talking about the current developments, just to differentiate that what we're talking. And yeah, I hope you have a good amount of cuff. So let's define the terms. It's customary to define the terms what we are talking about. So cosmology is a branch of astronomy concerns with the birth and evolution of the universe itself, how universe is formed and how universe is evolving as we see and as we observe. While the astronomy is a granddad and it itself is a study of heavenly objects like stars, clusters, galaxies. Um, so let's see how cosmology got evolved into. So since the time immortal, humans have been wondering about what is this all about, how this is universe came into the existence and what's going to happen next, how these structures are formed, how did we evolve, how did life evolve on the earth, how did earth evolve and things like that. So there's a lot of history into it. Just picked a few important events there. So let's see. So in Indian mythology, we see this reference of how this universe came into be. So especially in the first Veda, Rig Veda, there's a mention about Hiranyagarbha, which is a golden embryo, which was floating around endlessly, and then eventually gave birth to the supreme God, and then the earth, heaven, and the Pataloka. So that's way back in 1500 BCE. That's where we have the concept about the universe as such. And then of course a session in cosmology cannot be complete with the mention of Big Bang. So Big Bang happened, yeah, it does, and then when it happened, it happened with the bang, and that's why it's called Big Bang. And then eventually everything that we see here, just born out of that event. And when Big Bang happened, time was born, along with the matter that we all see here. And to extend that, we do have, our body has, most of the atoms, born in that event. That's why we have a living proof in ourselves. So as you can see here, the initial, the bang what happened, there was because of quantum fluctuation, and then there was a huge inflation, which is a rapid expansion. And then eventually there was the dark ages where there was no light, and then eventually, yes, there was a light, and then the structures formed, stars formed, galaxies formed, galaxy clusters formed, and planetary disks form around the stars, and then eventually we have planets, and then we have life. So this, as we know, of the observation and the calculations, this all happened in the 13.8 billion years ago. Now, what do we also see that in the recent times, the universe is expanding. The way we see that is when we observe a closest galaxy or a star, it is going away from us, and then so for the other stars and galaxies as well. So wherever we look, we see that everything is moving away from us. It's receding from us. So that's the that we call as expansion of the universe. And then we also see that when we measure it, how fast they are receding away or how fast they are moving away, we do see that, the day by day, as the time passes, the stars and galaxies are moving away pretty fast. And then that's the acceleration of inverse acceleration expansion. This accelerated expansion of the universe, and as we see that, this is, the scientists have thought about it, how it's possible, and then eventually they coined the term called dark energy. Where the term is a little bit misleading, but dark means we can't see it, we cannot actually measure it. So we do see that there is after effect of that dark energy, where we see the stars and galaxies are moving away from each other, and there is a companion to this dark energy, which is what we want to we would like to take a look at a little bit of more details. This is dark matter. So the name again is misleading. So there is nothing like a dark here. In fact, we don't know what it is, because we don't know what it is. So what we see is there is something called as dark matter, where all our ordinary matter that we see and infer are embedded inside it. The way we know that dark matter exists is several observations which happened in the 19th, 20th century. The biggest evidence came of existence of the dark matter is this rotation of the stars with respect to the distance from the centers in the galaxies. Vera Rubin, who was an American astronomer, discovered this, and what she did is she measured the rotational speed with respect to the distance of each of the stars within the galaxy, and it was expected to be like this. The less than as we move away from the center of the galaxy, the rotation speed should decrease. Actually, that's what we see in the solar system as well. The Earth is moving quite faster, when compared to, let's say, Pluto. The Pluto has not completed a single rotation at all, since it was discovered. So it's moving pretty slow around the sun. So the same concept we try to apply here for the galaxies and the stars within it. It doesn't seem to add up to the observed data. What we observe is this one on the right hand side, where we see that the rotational speed of all the stars within the galaxy, what we see is almost same. In fact, it's a little more. The only possible explanation that this happens is all the stars and all this visible matter is stuffed inside something called as dark matter, and there's a halo around the galaxies. The bigger halo around the galaxies, where we see it is also rotating along with the matter, and that's why we see that each of the star is almost rotating at the same speed, with respect to other stars. Now, we don't know much about dark matter, what it is made up of, and then how can we see it, or how can we determine it, how can we measure it. So, but we know a little bit about that. Since more than 50 years, there have been a lot of research is happening to find out what is dark matter and then what it's made up of. So, there are lots of contending theories about the dark matter. It could be particles, or it could be a fluid structure, solid or gases. The one thing that we know for sure, it has gravity. It acts gravitationally, especially on the other ordinary matter that we can see and infer, and it does not interact with the light. That's why we cannot see it with any means, with your telescopes, be it any visible light or infrared or ultraviolet lights. So that makes it very difficult for us to directly observe it and then detect it. But yes, there are lots of other indirect means of detecting it. It will not interact with any ordinary matter. It doesn't cause any reactions or anything like it. It will not break the ordinary matter, or it will not trigger any reaction into it. Nothing of that kind. And we don't know whether this dark matter is made up of same kind of material, or there are multiple flavors to it. When you see the ordinary matter, we do see, all of the matter is made up of atoms, and within the atoms we have protons, electrons, and neutrons, and then gluons, Higgs boson. And if you want to go and then categorize into individual, subparticles, but we don't know that whether the dark matter is of similar structure, it is made up of just coherent one single particle. And then what type of matter? We don't know, whether it is kind of like, electron, where we have the positive, negative charge around it, or a positron, which is a antimatter sibling of that. And also, we don't know about whether the dark matter interacts with itself. There are lots of theories and observations. One of the news that just broke last week, talks about this. So we're going to talk about that later. But we don't know yet whether the dark matter itself will interact with itself and then, produce some kind of a results or reactions. And for the dark matter, we don't know whether it has, the mass and the density of it, and thus we don't know whether it is a particle or a fluid. That's the first point. Now you might remember, right, even from the first slide, it's a journey into the unknown, right? So that's certainly there's a correlation there. Now, if we look at a little bit more detail about how this dark matter and dark energy fits into the entire thing, I think you have seen this pie chart. It's a famous pie chart explaining about dark energy and dark matter distribution across the universe. What we see here is that 95% of the stuff which is present in the universe, or 95% of the material which is made up of everything is unknown. We cannot see it, but only the 5% of is what we see it. All the stars, galaxies, clusters, planets, sun or sun like a stars, everything is made up in just 5% of that. 95% of everything is unknown, or we cannot see it directly. This is kind of like a weird thing, we are the situation that we are in. Now I would like to pause here for a second to see if we have any questions.
But I would want to know also, how did we arrive at that percentage in the previous slide?
Yeah. So this is mainly from the observational data. So as I said, we cannot detect the dark matter, we cannot detect dark energy directly, but there are lots of indirect observations that we can make. One of the indirect observation that we see is the gravitational lensing and like that. So we will see that in the upcoming slides as well. So what we do is we try to measure the concentration of dark matter around the star or inside the galaxy, and then that's how we can estimate how much of dark matter or dark energy stuff is there inside a galaxy, and then we can do a similar observation of multiple galaxies, and that's how we can estimate this 95%.
Or just we have one more question from Anmol. Yeah, if it is said that dark matter has gravity, so it should have mass and density. Yeah, can you please clarify that? Yeah, in your previous slide you had mentioned that it has mass and on something on that.
Yeah, if we try to compare with the normal ordinary matter that we see, and then try to say, okay, it might be made up of similar structure, similar matter, or maybe like similar particles, maybe some other particles that we cannot see. Then if similar lens, if you compare, yeah, ordinary matter does have gravity, and then dark matter also does have gravity. Then it makes sense to have dark matter particles to have mass and density, but the biggest problem there is we do not have any evidence or do not have any theoretical proof that they do. That's the reason I said it ought to have mass and density for sure. Because that's how we see. If we say that dark matter is a halo, it exists as a halo across the galaxies, and then all those individual stars are embedded inside it. So it needs to have some kind of a structure, some kind of a mass to hold those stars. Yes, you are right in the sense that it needs to have that mass and density. But yes, but we, as I said, we need to detect it. So if let's say if we ask questions saying that, okay, dark matter does have mass, okay, that how much is a mass? If you take a 1 kg of ordinary matter and 1 kg of dark matter, whether its mass same or different. Any other question, or we can move on?
Yeah, I think Sundar just provided one clarification there on how we are coming up with that mass number. It's simply by looking at the after effects of that phenomena and plugging that into a data simulation and then guessing that it should be the mass.
Yeah, yeah, true. And there are lots of dark matter simulations and then studies as well. Yes.
Yeah, you can continue on.
Okay. Cool. So let's look at gravitational lensing. This is the phenomena which we observe, postulated by Einstein and then verified observationally. That what happens is if we have multiple galaxies and then it happens to have like two galaxies around the line of sight and then one galaxy is behind another, we do see this structures called as Einstein rings, and then that particular phenomena is helping us to measure how much is the dark matter within a galaxy. So what happens is when as the light travels across the universe due to the large distances and due to the Doppler effect, the shifts its frequency, and then basically its color it becomes reddier than what it used to be earlier when it started from the galaxy. So that we can see that when it comes to the Earth and we observe from telescope, something like the MLMS telescope here, we do see that the entire the photons which are coming out of the background galaxy are redder than the foreground galaxy, as you can see in the picture. So one thing is this is helping us to look at the properties of background galaxy, but it will also help us to look at the dark matter content or dark matter distribution of the foreground galaxy. As we know, light bends because of the gravity. Light always bends across the corners that we see. If we see our shadow in the bright sunlight, we do see that our shadow has a fuzzy border. It doesn't have a sharp border. That's because of the bending of the light property on corners. So the similar phenomena happens here. So if that light coming from the background galaxies hits this matter and the dark matter of the foreground galaxies, it bends, and that's why we see that another ring-like structure, which is also called as Einstein ring. So this particular activity is used to measure the dark matter distribution, as I told. And in the recent, in fact, actually, it's the last week announcement from the Hubble data that one of the galaxy clusters, when observed using the Hubble and then analyzing the data which just came out of Hubble, that we see that we always used to assume that dark matter distribution is kind of like uniform across the galaxy. But this one particular example that we have here, it doesn't look like so. The dark matter is distributed across the galaxy in lumps. So if you see this video here, then it makes sense. So this is the the gravitational lensing I was talking about. This foreground galaxy and there's the background galaxies, all like the bent inlet structures. And this blue colored ones is the computational dark matter distribution. We don't see it, but it is just a computational one. As you can see, everything is like clusters together. And this is the one of the key discoveries that happened in 2020, and then that actually corrects or questions the observation that we had earlier, where we see that when we detected the dark matter, all the stars are embedded into the dark matter and they're moving almost at the same speed. We assume that it's going to be like cross. The distribution is like uniform, but this particular thing does not say so. It's just one of the case of the observation, but we definitely need to confirm this up front, and then learn more about the dark matter. Okay, so I will move on to the next one, which is also a recent development. But that requires explanation of gravitational waves. So I'm sure many of you have looked at this news since 2014 about 2012 about LIGO detector, LIGO stands for Laser Interferometry Gravitational Observatory. So here what happens is instead of measuring the light effects, we listen to the gravitational waves. So the gravitational waves are predicted by Einstein, and then they are caused, they are originated when two massive structures collided in the universe, something like two stars or two black holes, especially. So the way we detect is we just measure how the matter moves around or just vibrates, just similarly to the sound analogy. So if you have a big sound and then everything else, like for example glass shattering effect, so it's a similar thing. So in the LIGO aspect, what we have here is there are like two beam structures where the light passes inside them, and at the end of each beam we have a mirror, reflecting mirror, which reflect back the light which is emitted at the center. So the light that is used here is laser because it has a coherent and then it has a single frequency. It doesn't have all the other impurities. There is a source of the laser which it creates a laser, and then there is a beam splitter which splits the laser into two parts, and then each beam is sent in that arm, light arm, and then reflected back into the mirror, and then collected again, and then processed into a detector, which is here. So in ideal case, what happens is as the same light goes, splits into the splitter, and then goes into the mirror and reflects back, there will not be any let's say interference patterns on the detector. So we don't see any change here. It's the same light source that we see there. But if gravitational wave passes through, that results in a slightest elongation or contraction in one of the light arm. That will change the path of the light traveled, and then hence it changes its phase. How that phase interrupter will come in and join into the splitter again, and then eventually they'll produce a pattern, something like an interference pattern that we see. So when we throw two stones into the water, and then we see there is a wave-like structure, and then when they combine together, wherever there is a big wave combines, there is a huge wave, and then there is the light wave combines, there's no wave. The wave gets cancelled. So similarly, as light behaves as a wave, we do see the interface pattern. So that data gets processed, and eventually it's going to get converted into a wave-like structure, and that's how we see that then there's a gravitational wave, and then we can hear it. It gets converted into a sound. It's very, very fascinating to hear that sound of two black holes merging, and then how they produce the sound. So that's the key discovery that happened. So now because of this, we have expanded the observational capabilities multifold. There is a multi-messenger astronomy, not as it's called. So we observe the gravitational wave. At the same time, we observe the light-based observation as well, and we correlate. There are lots of findings that happened between the collaboration of LIGO and other telescopes around the world, and then we were able to detect a single event that happened from both observing gravitational waves as well as from the light. So there was another major news that happened in the last week itself. This is with related to the LIGO data. So when we want to find out about dark matter and model it, there are lots of candidates about how the dark matter would be. There are lots of theories around it, winds and all. So a lot of research is going on, and one of the theory suggests that there is something called as primordial black holes, which originated during the Big Bang, and they are distributed around the universe, and those are the dark matter candidates. So this theory was, proposed quite a long back, about 60s or so, and then there have been a lot of research happened, but there was no observational evidence for this theory. And it happened so that we now have a chance or a promise about this theory might be the one which defines the dark matter. So in the recent times, LIGO observed the collision of the black holes. It usually does that. And then what we see is there was one particular collision that happened between a black hole, which is of 25.6 solar masses, like 25.6 times the sun mass, and 2.59 solar mass. That's the least mass which ever observed in the LIGO, and in other ways also. So we couldn't detect these kind of black holes indirectly because because of the low mass that they have. And this actually rekindled the interest about this particular theory, which says that dark matter could be of primordial black holes. And what we see here is if we can detect black holes, mostly likely LIGO, which which are of close to the solar mass, one solar mass, and probably those kind of the black holes, that we can say yes, they do exist and they could be the right candidates to define the dark matter. So this is the recent development that happened. So again, there are lots of research still going on here, and even LIGO is improving its sensitivity, and LIGO is expanding. We have two in US detector. Detector in two, but there is one more in Italy, and there is one more that went online in Japan. There is also a LIGO detector being constructed in India as well, near Pune. So if we have good sensitivity of those detectors, I think we may be able to detect the primordial black holes through the LIGO. Okay, so that's, I think those are the two recent developments that I wanted to share in this thing. I try to balance out the history and the basics versus what's currently happening in the cosmology world. So hope it was a good session. So, and maybe I'm sure you might have realized I missed multiple aspects about cosmology and the current situation as well, especially the quantum mechanics and the quantum gravity. But I think that itself requires its own session altogether. So maybe I can keep that in the follow-up session. But for today, I think this is what I wanted to share with you all. And thanks for your time, and hope it was a good Sunday afternoon spent. And I'm ready to take questions. And just this first few references, if we need to follow the current developments which are happening, there are lots of resources out, but these are the ones which I usually follow. Jim A. Khalidi, he's a famous theoretical physicist and public coordinator. Usually, host talks in BBC radio shows. They are live, and you can see them on the YouTube. And that he has written two books. There's multiple books, but these are the two books which are quite popular, and then you would really get fun of reading it. Basically, first is The Word According to Physics, and it defines the basics about the cosmology and the quantum gravity there. And there's The Life on Edge, which mainly talks about quantum biology, which is a recent, highly researchable subject. We do see that there are lots of theories which proves or which indicates that even the quantum effect happens inside the living organisms as well.
Oh, thanks for the. I have one question in the previous slide. Can you show that?
Uh, sure.
Yeah.
Yeah.
So here, does this the right picture? Does it say that the kind of detection that has been done by LIGO that uh, uh, yeah, like the black hole of 149 solar masses, was it detected by LIGO, and was it not detectable by any other source?
So this actually chart contains both observations, detect with X-ray, so it's a direct observation, and the 149 was the largest one, which recently was confirmed by LIGO. The observation that did happen in May 2018, but the observation was confirmed recently in the month of July. So that is the biggest ever black hole that detected by LIGO so far. Um, so yeah, I mean there are lots of research going on there, and then there are lots of observations also like followed to just to confirm what LIGO detected. Yeah, but as
Okay.
these are black holes, there are a lot of limitation about how do we observe them. I mean, again, we can only observe the after effects of it. Let's say if there's a star nearby, we can observe how the star moving around the black hole by observing the rotational speed of it or the speed of it, and also if there's a black hole which is eating a nearby star, we can know the accretion disk, and also yeah, I mean those are observation things, those are only detected by X-rays. So
Okay. Yeah, so it seems like because of LIGO, we are able to now detect more number of black holes, and especially during the time of their mergers.
yes, that is correct. That is absolutely correct. So especially the ones which are having a lower solar masses, this could only be detected by LIGO as of now. I mean, given the technology, the observation technology that we have, it is quite difficult to observe those.
Yeah, I was just waiting for you to finish. The thing is, the mass plot that you're looking on to the right, those are the theoretical predictions, okay, as compared to what we have, what the LIGO has observed. So the expectation is two black holes merged, coalesced, and they formed a bigger black hole and gave out that particular detection of gravitational wave. So the numbers are somewhat a limitation on what could be its mass. It could not be bigger than that, obviously. So they did not detect the black hole itself. So that would detection of black hole would need, like Vadiraj was mentioning, it would require multi-wavelength confirmation. Could be X-ray, could be gamma ray, or could be any other frequency verification and follow-up studies. But it is also possible that we might never be able to see this particular black hole of 149 solar mass because there is no matter for it to, suck and emit electromagnetic radiation. But
Okay.
we just know it is somewhere out there with that mass.
Okay. So the effect of, I mean, like 65 solar masses black hole and 85 solar masses black hole. So this number has again been derived from before and after that merger event, right?
Exactly, because they would have observed this what is called as ringing time,
Mhm.
and so if I've been observing that particular set of noise coming from that region for say 10 minutes, and the this merging happened in the last 10 seconds. So combining that 10 minutes, 10 seconds data, they'll be able to determine what could be the rough sizes of limits on the sizes of two black holes or black hole neutron star or neutron star pair that coalesced into forming a bigger object. and whatever energy they detect out of the gravitational wave recorded on the detectors, that would get added on, that would get subtracted from these masses to determine the rough mass of the final object that is formed.
Oh, okay, got it. Yeah.
So, because we expect that from Einstein's energy mass equivalence, we know that this gravitational energy would have come because some of the mass would have got transformed into the energy at that point of time. So they just do back calculations to get limit on the.
Yeah, that answers my question. Thank you, Vadiraj, once again for your time and having this insightful session. It has been a good learning for me as well to understand the latest advancements in the field of cosmology and latest discoveries also. Yeah, thank you very
Great.
much.
Okay.